In this lecture, we will introduce abstract data types. Specifically, we will be talking about the list abstract data type. Recall that an abstract data type, or an ADT, is simply a set of objects that's grouped together with some set of operations that we can perform on those objects. Notice that I didn't say anything about how the operations are implemented. We're just told what those operations are, but we're not concerned right away with how we actually implement those operations. So let me give you a couple of examples of abstract data types. We have things like lists, sets, graphs, and so forth. One way you can think of an abstract data type is think of it as like your own data type. Here you can define the data that's going to be stored with that data type, and you can define the operations that can be performed on that data type. So for example, maybe if we define a set ADT, we can include the set of integers. So we can say we're only storing integers, and we can define operations such as adding something to the set, removing something to the set, or even checking if an item is contained in there. So we can have like a contains operation that returns true or false if something is in that set. To implement an ADT, we can use Java classes because it's really convenient. Because think about how a Java class is set up. You decide what types of data and operations you're going to have in the class. So the class simply defines all those operations for an ADT. And then we can have a client that would call the appropriate methods, or we create an object of that class, which would be an instance of the abstract data type, and then we can call all those operations, call all those methods. And if we need to make any change to the implementation, then all we need to do is just change the appropriate method. We can just go into the class definition, we can change the definition of a particular operation, and we don't have to do any substantial changes. The other thing I should mention is there's usually no rules that state what can and what cannot be, or what must be part of an ADT. With that said, it's usually a good idea to include things such as error handling, because you don't want exceptions to happen. So if you try to put in a value that should not be in there, you should be able to handle your own errors, and things like tie breaking are usually a good idea. We're going to look at 3 common ADTs in this class. We're going to look at lists, stacks, and queues. We're also going to look at how we can actually implement these ADTs in different ways. So what we're going to see is we can use different underlying data structures for implementing these different ADTs. And if we do the implementation correctly, the user is not going to have any idea what the underlying data structure is. Now, if they look at the class, they would see that. But if they look at the client and the list of operations that could be part of the ADT, the user shouldn't be able to tell whether we use one data structure for the ADT or if we use a different data structure for the ADT. Now, we just mentioned that we're going to be looking at some different underlying data structures. But you might be thinking, well, arrays seem to be pretty effective, so why not just use them for everything? The problem is that some of the operations for arrays are slower than what we would like. For example, searching is going to take O of n time if the array is unsorted. Now, if the array is sorted, then that takes O of log n time, but inserting into a sorted array takes O of n time. And then deleting takes O of n time regardless of whether the array is sorted or not. So these are a lot slower than what we would want in an underlying data structure. We would like to have a data structure that does all 3 of these faster, whether it's in constant time or O of log n time. And we will look at data structures that accomplish this, that are more efficient in terms of time. But we're also going to see the cost of actually achieving those efficient running times. Another issue with arrays is that the size of the array is fixed when we first create them. This means if we need additional elements beyond the maximum size of the array, we're going to encounter some problems. Now, there are ways around that, and we will take a look later on at how we can address that issue, but it's still a problem if we need more elements than the amount of space we've allocated for the array. And then another issue with that is if we don't use all those elements, then we're just wasting memory. We have this allocated memory that doesn't do anything. It's just kind of sitting there and looking pretty. So we will be looking at some more flexible data structures. One such example would be the linked list. Now you might be asking, well, couldn't we just use the vector class in Java? That lets us expand an array as we need to, so we can add elements and remove elements without allocating additional space. And yeah, that does work, but for the basic operations, we are going to lose some efficiency in order to have that more flexible memory capability.